Hey everybody, welcome to AE 430, Stability and Control Systems Analysis and Design. Right now we're going to do Routh tables. So we're given this transfer function, 1 over 2s4, so on and so forth, and it's in this unity feedback system. So determine if this system is stable, basically, is all we have to do, but we have to use a Routh table. So the very first thing we have to do in order to be able to use a Routh table is you have to have a closed loop system. So we have to complete the block diagram algebra as part of this unity feedback using this transfer function. Now, when you have a unity feedback system, you should all know this, you just have 1 over GH plus 1. And that's how a unity feedback system works. In this case, we don't have an H, or the H in this case is 1 for the unity feedback, so you can basically ignore it. So we're going to end up, if you do that math, as 1 all over 2s to the 4th plus 5s cubed plus s squared plus 2s plus 1. And that is your closed loop transfer function. So we've gotten rid of this little feedback system and we're just down to a single block basically. So that's what you have to end up with before you can use a Routh table, a complete system that's reduced as far as it can go. So when using a Routh table, what you do, all you have to do is look at the denominator. The numerator is not necessary for anything at all. You can just ignore it, cross it out, get rid of it however you want to. And looking at the denominator, we see we have a power of 4. So we're going to have 4 poles. Something to note, if you do your Routh table and you don't end up with 4 poles, then you know you made a mistake, and you need to go back and find it out. Since we're just looking for stability, that's not terribly relevant, but just as a check for yourself. So setting up our Routh table, you go s to the 4th, s to the 3rd, s squared, s1, s to the 0. And then setting up the first column, you go s to the 4th, the coefficient is 2. Then skipping over, s squared, the coefficient is 1. Then skipping over again, the number is 1. And then for s cubed, we've got a coefficient of 5. Skipping over 1, 2. And then from there, skipping over 1, 0. So we filled out our first 2 columns. Now going down here and actually doing the matrix math that we have to do. You set up your matrix. It's negative matrix, all over number. And the way you set up the matrix is the first column of the matrix is the first 2 numbers directly above where you're setting up the matrix. And these will be the first column of all your matrices across this row. And you'll see how this works in a second. And then the second column of your matrix is the 2 numbers above where you're solving for your matrix, but 1 over. So basically this is going to be our square of the matrix. So 2, 1, 5, 2, and then it's divided by the lower left-hand part of your matrix. You'll never have anything larger than a 4x4 matrix when doing this. This is as big as it ever gets. So divided by 5, and if you do that matrix math, which is 2 times 2, 4, minus 5, by doing the cross product here, and you'll end up with 1 over 5. And then moving over to our other one, negative again, you keep the first column, 2 over 5. This is constant for all the matrices across here as we go. And then you grab the 2 numbers after the column that you're working in. So 1 and 0. And then again, the lower left-hand corner, divided by 5. Now here's a trick. Since you have a 0 in the lower right-hand corner of this matrix, the value that it's going to equal is the number in the upper right-hand corner. So pretty much, you can just shortcut right here and just go equal to 1. But if you want to do the math, just go ahead. 2 times 0 is 0, minus 5, positive 5, divided by 5 is equal to 1. Oh, it's your upper right-hand corner value. So if you've got a 0 and a value over here, this is the value that it's going to be if you're using this column. So just a little trick there, shortcut. Okay, our final column here, 2 and 5. Again, always using the first column of the 2 rows above. And then you've got 0, 0. These zeros come from out here. They're out in imaginary space because you have to have something following. But in reality, it is 0. These would be s minus 1 and s minus 2 to minus 2 or something like that. So that's how that would work if you wanted an algebraic explanation. Then divided by 5, and that's going to equal 0, because you've got 0 times plus 0. So, that's pretty good. Now, when you're working with a Routh table, sorry, can't pronounce the word, a Routh table, what you do is it is going to be stable so long as there are no sign changes in the first row. So we're looking for a plus, 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 or a minus, 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 minus. Since these first two values in the first column were positive, we're hoping that all the other values in this column will also be positive. And so far we're getting away with that because we have a positive 1/5 here. So we're going to keep on going through here. If we have a sign change anywhere in the table, it's going to be unstable and we can stop right there. So moving here on to the next part, we've got a negative. Our matrix is the two values above. So in this case, it's going to be 5 over 1/5. And then using these two values over here now, the column to the right and 2 above, 2 and 1, and then divided by 1/5. Now, if you do all this math, it's going to be equal to negative 25 plus 2. This was the shortcut that I did. 5, 1/5. What you do is you can take this 5 up here and multiply by what the interior of this matrix is when you do the cross multiplication, and that's how I did that. And then that is equal to negative 23. Well, hey, remember how I said if there was a sign change, we immediately know it's unstable? There's a negative. So we know that it's unstable. Unstable immediately right there. With a sign change, immediately means it's unstable. And that's why Routh tables are so handy, because you can fairly easily figure out if a system is stable or unstable. I'm going to go ahead and finish out this row just to give you a little more practice with Routh tables. So if you want to see how this goes, it's 1/5, negative 20, oh, oops, sorry. Jumping the gun, that's the lower column. 5. Jumped a little too far ahead there. 5 over 1/5, negative over here. First two values over here. And then we've got 0 over 0, which are these two values over here. All divided by 1/5. That's going to be equal to 0. And then if this one is equal to 0, you immediately know that this one is going to be equal to 0. That's just a given, another trick with the table. So then moving down here one more time, I'm going to just do this last value here real quick. So you're going to end up, with 1/5, negative 23. These two values right here, the two values immediately above. And then these two over here will make your next column, 0. All divided by negative 23. If you do that math, you'll end up with negative 10. So that is about all there is to it. Routh tables are pretty darn easy. Let me double check this real quick, actually. 0 minus 23. Oh, sorry, that's not negative 10. That's negative 1. Thought I was doing that. In my notes, I had something else kind of written there, but it was just a note in my notes. So that's negative 1 right there, because you have 0 plus 23 minus negative 23, which is plus, and then negative 23 over negative 23 is equal to 1. So a sign change again, actually. Make sure I did that right. Negative 23 plus negative plus. Okay, yes, a plus 1. So that's a plus 1. So that would be a sign change. If you wanted to know what those mean, well, this means you've got a sign change. You can go through and get the right hand and left hand plane poles now using that information. I'm not going to go into that, but you've got two sign changes, at least two poles in the right hand plane. So any sign change means a pole in the right hand plane of your geometric graph. So real here. We've got two poles out here in space someplace or wherever. They could be anywhere over there, but there's two of them. So there's our two poles. And that's kind of what your root locus plot would look like if you were to graph this. And that's how you do a Routh table to figure out stability.